Hello everybody. In this video I'm going to talk about the concept of acceleration. Let's define what acceleration is. Okay? So acceleration is basically how fast your velocity is changing. Okay? So for instance, if you take your car, for instance, if you're driving, there are three ways in which you can change your velocity. In other words, in which you can accelerate. Okay? And acceleration, by the way, includes acceleration, speeding up, or slowing down. They are both in there. So for your car, you can use the gas pedal to speed up, that you create an acceleration. You can use the brakes to slow down. That's also acceleration. Okay, just deceleration. And then you can change direction. You can use the steering wheel to change direction. So all those three will provide some kind of acceleration. Maybe the third one is kind of like hard to see, but once we talk about motion that's curvilinear, meaning like it's you're going around the curve, we'll talk about the cause of that acceleration. So acceleration is basically how fast you change your velocity. So if you think about that, is how fast, meaning like time, okay? You change your velocity. So change in velocity divided by time. Now how do you find change in velocity? Well, you just do your final velocity minus your starting velocity divided by the amount of time that it took to make that change. And that's pretty much what acceleration is. So I'll do an example here. So let's say I have an object, A, going from 40 miles per hour to 60 miles per hour. And let's say it does this change in 2 seconds. Okay? And I have another object, B, going at 70 miles per hour, okay, to 90 miles per hour, and it does this change in 4 seconds. Okay. Now, if you look at the first one, it changes by 20 miles per hour in 2 seconds. So you pretty much have a positive 10 miles per hour per second. Okay. So basically, what this means, if the acceleration is constant, if you keep changing at the same rate, it just means you're going to pick up an extra 10 miles per hour every second, which kind of makes sense here. If you look at the second one, you're picking up an extra 20 miles per hour, but it's taking you 4 seconds to do it. So now you're picking up 5 miles per hour every second. So you can see that in the first case, even though we were going at slower velocities, we had a bigger acceleration. So just don't confuse acceleration with velocity. Yeah, you might be going at a higher velocity, and when you're changing, your change is not as noticeable, it's not as great as if you go into slow velocities, but your change is great. So in this case here, the first one, even though you're going at a slow velocities, provides more acceleration. So because the change is happening faster. Okay. So I gave you the formula. Now let's see if we can find acceleration from a velocity time graph. So if you have a velocity time graph, and let's say my graph looks something like that. I'm going to throw some numbers here. This is 3, this is -5. I'm going to say this is 2 seconds, 3 seconds, 5 seconds, and 6 seconds. Okay. If you analyze this graph from 0 to 2 seconds, okay, there is no change in velocity. You're stuck at 3 meters per second. Let's just say this is meters per second and time is in seconds. So your acceleration here is 0 basically. Okay? In the second case, okay, you're going from 3 to 0 because the velocity at this point here is 0. The velocity at this point here is 3. So it's 0 minus 3 over, it took 3 seconds to do that, so it's -1. Which is really nothing other than the slope of this line here, of this segment. Okay? And you can do the same logic and you can find that the acceleration is equal to the slope in a velocity time graph. Okay? That's how you find the acceleration. Now, for this level of physics, all the velocity time graphs will be segments. In other words, they will not be curves. Okay? So the slope is going to be easy to calculate. If you look at the first 2 seconds, constant velocity, okay, from 2 to 3, it looks like you're slowing down. You go from 3 meters per second to 0. But you have to be careful here. So from point A to point B here, in other words, between 3 and 5 seconds, you're going from 0 to -5. But in terms of speed, you're going at 5. Basically, what this means is just at 5 seconds, you're going at 5 meters per second in the negative direction. So the negative for us just means direction. So -5 is bigger than 0 in physics, okay? Because you're looking at it as a 5, not as a -5. So from 3 to 5 seconds, you're speeding up, okay? And from 5 to 6, okay, you're slowing down because you're going from 5 to 0. So the bottom line is this. Each time your curve or your graph approaches the time axis, in other words, you're approaching a velocity of 0, you're slowing down. Each time you're running away from the time axis, you're speeding up. Okay? Based on this, you can see that from 0 to 3 seconds, we're moving in the positive direction. And the reason for that is because all your velocities in the first 3 seconds are positive. You take any point here, projected on the y-axis, you're going to find out that all those numbers are positive. Each time the graph is, in a VT graph that is below the time axis, you must be moving in the negative direction. Okay. All right, now the next thing I'm going to talk about is how do we find displacement from a velocity time graph. So if I have a VT here, I'm just going to throw some numbers here. So I'm going to say this is 5 seconds. This velocity here is 10 meters per second. Okay. So here it looks like I'm going at a constant speed. I'm covering 10 meters every second. So in 5 seconds, I should see that I covered 50 meters. Now if we do this area here, this rectangle, it's 10 base times height, so it's 50 meters. So the rule is this. Displacement can be found, okay, by calculating the area in a VT graph. So I hope you remember that. Okay, we'll take notes on this in class, or you can take notes now in your packet. Now what happens if we have some weird shape? Okay, so let's do something different. Okay, so let's say I start here, I do that, and I do this. Okay, so 3, 2, 3. Let me make sure I'm doing this right here. I'm going to say 5 and 6 here. Yeah. Okay. And I'm going to say 6 seconds. Okay. This is meters per second, and this is time in seconds. Now, if I want to find my displacement, all I have to do is find these areas here and add them up. Now, how do you find these areas? That's up to you. If the shape looks weird and you're not familiar with it, you can break it into easier shapes. For instance, this shape here, it's a trapezoid. So if you don't know the formula for the area of a trapezoid, you can break it into a box here, a rectangle, and a triangle, which you are familiar with. This is just a triangle. This area here, after you find it, for this whole part, is going to be positive. And the reason for that, because between 0 and 3 seconds, you're traveling in the positive direction. Okay. The area down here, and again, this is in a VT graph, the area down here is going to be negative because in this part of the graph, you're traveling in the negative direction. Okay, now I'm going to give you a shortcut of how to do this stuff. PV, not T. A. Okay, position, velocity, acceleration. Okay. Now, if you have a position time graph and you do the slope, that's going to give you a velocity. And slope just means the steepness sometimes, if you only compare and you don't want to find numbers. If you have a velocity time graph and you do the slope, you get your acceleration. Now there's another thing going the other way. Okay. I'm going to leave this for now. I'm going to talk about V and P. If you have a velocity time graph, and if you do the area under the curve, I just did that like 2 minutes ago, you don't find position, you find displacement, which is the change in position. So this, maybe I'll put a delta here. Okay? So when you're reading it in this direction, you have to put a delta. If you have an acceleration time graph, okay, and you do the area under the curve, and always consider that anything below time axis, the area is going to be negative. So if you're below the time axis, if you find the area in an acceleration time graph, it's not going to give you the velocity. It's going to give you the change in velocity, because you don't always start at zero. Okay. Now I'm going to show you I'm going to write the formulas for accelerated motion. I'll explain every term and we'll do the problems in class. So if you want to find the speed after a certain amount of time, okay. So VF stands for final velocity. VO stands for initial velocity, meaning like when the clock starts, O for 0. Acceleration and time is T is the time it takes to go between these two speeds. If you think about it, this is nothing other than what I did earlier. So I said A is change in velocity over time. And the change in velocity is the final velocity minus the initial velocity. So if we manipulate this equation a little bit, I put the time here, right? And if I move the V initial or VO here, these two equations look the same. The other equation is, so in this equation here, you're not going to be able to use it to find the displacement. It's not going to help you. The other one is the one that can help you with the displacement. So displacement is initial velocity times time. To do this amount of displacement plus 1/2 acceleration times time squared. The other one is delta x, which means displacement is the initial velocity plus the final velocity over 2 times the time it took to go between these two velocities. Now, all these equations are only valid if your acceleration stays constant. And it will stay constant for this year. Okay, the last one is VF squared, final velocity squared, is the initial velocity squared plus 2 times the acceleration times your displacement. Now these formulas are in your formula sheet. Which one you're going to use, it all depends on what you have. So I always recommend that you write your known variables and you put the unknown next to them. And based on that, you look at these formulas and figure out which one will help you solve the problem. With that said, thank you very much. See you later.